Okay, we ended our lecture last week with conditional probability. Conditional probability occurs very often, and then one of the powerful tools that we are going to introduce to you is the Bayes two formulas, and we will do it in a minute. And then another common problem that in conditional probability is to inverse it. I will mention what do I mean by this. Okay. Okay. So there are many occasions that we have some information. The information that event A has already occurred, and we wanted to update our estimation of the probability of B, knowing that A has already happened. This often is the case. So the definition, we mentioned it. The key would be we do assume probability of A has to be positive, and that it is the probability of the intersections. So you have to watch out for the order, whether you are given A or given other things, because the given event, the probability goes to the denominator. So if you switch it to probability of A given B, it would be the same numerator, but the denominator would be probability of B. So this is crucial. We probably won't mention it, but this is mathematically a mistake if you, mess up with the denominator. And usually the interpretation is wrong. You can watch some of this. This is called the prosecutor's fallacy, meaning that very often we are calculating the probability that, say, suppose the prosecutor is saying the probability of someone is guilty. So this is the probability based on the evidence. But very often the prosecutor's argument is thinking of the reverse, meaning that the probability that his statement is correct given the evidence. So, but the probability very often is the other way round. So that is a very common mistake in legal setting. The prosecutors commit this kind of mistake. It's called prosecutor's fallacy. You can Google it if you are interested. So this can be have a very serious consequence, because if you misinterpret the probability, you are off to a very large extent. Okay, so we are interested in what is the probability of the sum of the two rows is even, and that if I know the first die give me a 5, so without the conditioning, we actually have this array of events. So we arrange it in a nice table in this way. So we can just calculate the probability of having the sum is even. So the sum is even will be this one, and this one. Each row will have 3. So that is why it has 18. And so this is just the table. But this is where the extra information helps us. We know something now. We know that the first row is 5. If we know that the first row is 5, then the first 4 rows would not be possible. So we have to strike them out. And then the last row is also not possible. We have to strike it out. And so as a result, we are left with this table only. And now we are interested, knowing that given this row, meaning that the first row is a 5, and you want it to be even. So there are only these situations, and these situations. So as a result, this is 3/6. And now we can just substitute the definition into it, and this would be 3/6. All right. So you can think of the conditional probability involves three terms. One is the conditional probability itself. The other is the probability of the joint event to happen at the same time, and that you have the probability in the denominator. You can manipulate this three variable in whatever order to calculate the other one. So what it says is that if you know two quantities, and so you will be able to calculate the third quantity. Okay, and we will introduce this as a multiplication rule. But before we do so, we wanted to see it from the framework of probability. And this is a reduced sample space. I will just read it out, but then I will draw a diagram to illustrate the point. The conditional probability of B given A can also be read as the conditional probability that B occurs given that A has occurred. Now, this is the, the proper way of stating the conditional probability. But very often in daily life, or people who are not really into this probability area, they may be saying something a little bit different, all right? And that is where I mentioned about the prosecutor's fallacy occur, is because they don't write it down as precisely as this is the situations. If you write it down precisely like this, then the chance of making a mistake of making a mistake in the denominator will be minimized. Okay, and the argument is this: since we know that A has occurred, think of A as our new sample space. So your sample space is, originally sample space is the all possible outcomes of an experiment. And now, because you know that A has already occurred, you can reduce your possible outcomes. And this is one possibility to think of it this way. Okay, so this is your entire sample space, and you are interested to calculate the probability of B. All right, so this is just the probability of B. But then on the other hand, this is the same B here, the same sample space. But now you know that A has occurred. So suppose A is this part. So this is where the slide was trying to explain. Is now your sample space, you can ignore this portion. Because this is where, because you already know A has already occurred. And so this is where the B will be, because this part of B will not happen, because we know we are now reducing everything here. And that is why we have the definition. So this is giving an explanation of why the conditional is defined in this. So the numerator is explaining this portion where A intersect B. And now sort of like you have to normalize it. That is our axiom number 2. Because this portion is no longer with probability 1, so we have to blow it up by dividing this probability so that the entire thing here is now probability 1. So this is why we have to divide it, because this is in relation to this piece. All right? Okay. All right, so we proceed with another example. Suppose we have two fair dice are rolled, and given that the first die is less than 3, what is the conditional probability that the sum of the two dice is more than 7? So what one way to solve it is that, again, another way, slightly different from here, you just use the same table, and then you just draw down what are the corresponding outcomes that corresponds to your description here. But let's try this. Let B be the event that the sum of the two dice is more than 7, and A is the event that the first die is less than 3. So we consider the reduced sample space because with the 12 points, so more than 7, or less than 3. Okay, so we have, what it means is that the first die must give you either 1 or 2. It cannot give you anything more. So that is why I have these 12 outcomes. All right, 1, 1, 1, 2, up to 1, 6. This is for die having die 1 having a number 1, or die 1 having a number 2, and then I don't care about what is the number for the second die. And there is only 1 point here in the reduced sample space that gives a sum more than 7. So as a result, this is 1 over 12. Okay. Now in a card game of bridge, if you know it, then you will appreciate this kind of questions are very important when you are, let's say you are dealing a card. The 52 cards are dealt out equally to 4 players, so meaning that everyone will have 13 cards. And the bridge game is a partnership game where the North-South form a team, and then East-West form another team. Now, because suppose North is the I forgot the name, the dealer or whatever. He's the player, and then South would be the dummy. And so if the dummy will lay down all the 13 cards. So in other words, everyone know actually 26 cards, all right? But for the North, he can count that he has a total. He and the South has a total of 8 cards, 8 space, and very often, sometimes you have to decide whether the distribution of the remaining 5 space is even or not even. In this case, we are thinking of whether East has 3 and of the remaining 5 space. Let's say if East has 4 space, and if North is playing the card, and if South has a big spade, one possibility is depending on how East play the card, then South will whether play a bigger card or a smaller card. So calculating this kind of probability is useful. Now, of course, calculating this takes time. People in the business, they basically memorize it, or they play so often that they have an idea of the probability. So let's do the calculations. We will work with the reduced sample space. Now, since North-South has a total of 8 space among the 26 cards, then there are total 26 cards, 5 of them being spaced to be distributed among the East and West hands. All right, so this is the situation. And so the conditional probability that East will have exactly 3 space. First of all, this is the number of ways of dealing 13 cards out of 26. The 26 cards of the East and West combined together. And I want 5 of the remaining space, 3 of them go to East, and then the remaining 21 cards in order to make up the 13 cards of yeast, so yeast has 3 space, so that means he has to have 10 cards from the other 3 suits, so and which is make up 21 cards. So this is this. So the probability is 0.339. You might ask about the other probability. Yeast will have 4 spades, or yeast will have all the spades, and so on and so forth. Now, of course, depending on the value of the spades, you can make a guess whether yeast, make a further guess whether yeast will have all the 5 spades, because suppose the spades are of high values, then you can, from the bidding process of the bridge game, you will have a sense whether yeast will actually have, all the spades, all right, and so on and so forth. If you play bridge, these are very natural questions that you will ask. Okay, another questions, another example. A couple has 2 children. What is the probability that both are boys if it is known that they have at least 1 son? Okay, let us assume that it is equally likely to be a boy or a girl for every newborn baby. The fact is, it is not exactly equal. I think it is very close to being equal, but I think girl is a little bit with a high probability in Singapore, if I'm not mistaken. But of course, the probability is estimated. So let E be the event that the couple will have 2 boys, and the event F is that they will have at least 1 boy, 1 son. So it is boy, 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 girl, girl, boy. And so E intersect F would be a boy and boy, and so on and so forth. So, so you just do the enumerations out of this. All right, so it is 1/3 here. For myself, I would recommend to go through the probability of the fraction here, meaning that you calculate the probability of this one. This is because E intersect F is equal to E, and you calculate the denominator separately, rather than looking at F having 3 outcomes, and then you are only looking at 1 outcome, and then assume that these 3 outcomes are equally likely. Once in a while, something may go wrong in this assumption, one of which I wanted to bring in the Monty Hall problem, seeing the equally likely argument will break down in the argument. Not that equally likely is wrong, it is the assumption of equally likely is problematic over there. So the following data were obtained in a study. They basically want to see, you will see something like that later on when we do statistics. What the question is trying to drive at, or why researchers are collecting this kind of situations, is to see whether smoking or the extent of smoking has anything to do or associated with hypertension. All right, this is crucial. Now, a lot of these studies can't prove that smoking causes hypertension, but they can show whether it is associated. Now, if it's not associated, then definitely smoking has nothing to do with hypertension. But if it's associated, it might be a contributing factor. So this kind of situation is what we usually call a two-way classifications. For each of the subject, 180 of them, you have 2 classifications of the same subject. One classification is the smoking status of the subject, and then the other is the health status in terms of hypertension, whether yes or no. All right. So as a result, you build this kind of a table. So the table you actually have would be 21, 36, 30, and these 3 numbers. These are what we call the marginals. So these are the row total. So you add up the entire row here, and these are the column totals. You think of it as marginal, the margin according to the non-smokers, and then this number is the grand total. I think when we are dealing with contingency table, we will come back to this kind of notations. If one of these individuals is selected at random, find the probability that the person has hypertension. Okay, and then part B is has hypertension, given that the person is a heavy smoker. And the person is a non-smoker, given that the person is experiencing no hypertension. So we'll just work out the probability. We assume that each of the 180 persons is equally likely to be selected. This is the assumption here. All right, assuming the 180 persons are equally selected, and let H and H complement denote the event that the selected person is experiencing hypertension or no hypertension, respectively. So the required probability is given as probability of hypertension. So we go back to the table. So we are looking at the hypertension. So there are 87 subjects out of 180. Since we assume the selections, the choice is random, meaning that everyone stand the same chance to be selected. So it would be 87 out of 180. So that is the probability here. And let A be the event that the selected person is a heavy smoker. So the required probability is given by the probability of having hypertension conditioned on that he is a heavy smoker. So this is by definition probability of the joint event having hypertension and a heavy smoker. And here we can go back to the table. So you go to hypertension and heavy smokers. So these 30 people belong to being heavy smokers and having hypertension. This is 30 out of 180. So that explains the denominator here. And if you go back to the same table, there are 49 people experiencing, they are heavy smokers. So you will have this. So this ratio is somewhat like 60%, all right? This is having hypertension. If you do not know he is a smoker, is slightly less than 50%. So of course, we need to quantify this. Something like 60% is it exceedingly higher than the 50% here? If it is, then being a heavy smoker sort of increase your likelihood to have to experience hypertension. So let B be the event that the selected person is a non-smoker. The required probability that he does not have hypertension, given that he does not have a hypertension, he's coming from the non-smoker group. And so we go through the table again, and it worked out to be 48 over 93. So it is, again, slightly less than 50%. So almost like 50% of the people among those who do not experience hypertension, they are non-smokers. All right. Okay, so this is the proposition. Basically, it says that conditional probability, when the event that you are conditioning on is fixed. All right, so let A be an event with this. This is the requirement so that my denominator makes sense. Maybe you should write down a remark that this A is fixed throughout, all right, in my thinking. then the following three conditions hold. So you are varying the B. So what it says is that for any possible event B, the conditional probability is always sandwiched between 0 and 1. A is fixed, B is changing. So this conditional probability, you think of it as a set function again. The set function is defined on all the other possible event B. And now if S is the sample space, then the conditional probability of S condition on A is equal to 1. And then we also have this. Now, if you look at this, this corresponds to entirely the three axioms or the three rules of probability. So basically, this proposition is saying that the conditional probability as a function in here, the variable is changing here. It is the probability assignment. Okay, we can give a very quick explanation or proof of why these three things. So the first one, this is by definition. So of course this number is non-negative, all right? Because it's the ratio of two non-negative numbers, or ratio of, one non-negative and then the bottom part is positive. And A-intercept B is a smaller event than A, right? So if you recall, smaller event, smaller probability. So this implies this fraction will be less than or equal to 1. So, so that establishes part 1. And then part 2, we spell this out. So, but remember that A is a subset of the entire sample space. So the intersection will be A itself. And so it is equal to 1. And now we have this. Okay, again, this comes from intercept A, probability of A. Okay, and so now you think of the intersection as multiplications, right? So and then the union as sum. So you can actually multiply it in. This is whatever. This might be the De Morgan's law or distributive property. So you take the intersection one at a time and then union back. So this is coming from the set equality. Okay, now if Bi, Bj are mutually exclusive, meaning that Bi, Bj has no overlap. So of course this will imply Bi intercept A and Bj intercept A are also mutually exclusive. Is that okay? Because the original bigger this Bi, Bj actually do not overlap. And now you're looking at the Bi, Bj intercept A, so you're looking at the smaller portion of the Bi, Bj. The smaller portion can't overlap. All right? So if they do not overlap, then we will have this. So this is by our axiom number 3, the original one. So I still have this. So I will have this. All right? And now I divide the things inside term by term. Okay, and then this is just the definition of the conditional probability. Okay, so that establishes the proposition 7. I think why I'm interested in giving you the proof is because basically it's very deductive in nature, and also it just making use of the definitions. Okay, is that all right? I think you don't need to copy line by line, just copy some milestones, and then it might be better that you can fill it in. This gives me the excuse to switch it. All right. Okay, so these are the propositions. And so this is just explaining the proposition, the meaning. So this means that if the assignment is in the dot here, as a function of the dot, as a function of events, satisfy the three axioms of probability. And hence all the propositions in the section 6 will apply to here, as long as your A is fixed. So what it says, for example, if you are computing the probability of B complement condition on A, it would be 1 minus the probability of B condition on A. That is the same as the probability of the complement is equal to 1 minus the opposite. But now all the probabilities are conditioned on the A. So you just replace your argument by conditioning on A. And then if B is a subset of C, then the probability of B conditioned on A would be less than or equal to the conditional probability of C conditioned on A. So you just add the condition on A throughout everything that you have. So that is why the earlier propositions have its generality, okay, and also because of proposition 7. Okay. A statistics professor is teaching both a morning and an afternoon section of introductory statistics class. We define the following events. The professor gives a bad morning lecture. The professor gives a bad afternoon lecture, and these are the probability. And he gives lousy lecture in both sections. It would be 0.1 here. All right. So we are interested in calculating this. These are fairly easy and direct. So the first thing is basically unconditionalize it. Okay, that is what unconditionalize it means. You spell it out as a fraction of the ratio, the ratio of two probability. All right, and remember that the denominator will be following whatever you are conditioning. So once you unconditionalize the whole thing, then you just apply the probability here to do the work. So I think I will just go through it quickly. So this is what I'm saying. So you unconditionalize it, all right? And so you have this. Now, this is just one method. The method here is actually a reflection of the remark in 2 slides before. Here, all the propositions in section 6 apply to here. So it's saying that I'm looking at the conditional probability of the opposite of B. It would be 1 minus the probability of the thing. And of course, I have to, in the context of the conditional probability. So I have this. And so I can recycle the result in part A, which is 1/3. And so I have 2/3 here. Now, here I have to do this. And this is quite a useful thing to think of. the probability of B intersect A complement is the part that is outside A but inside B. So it's sort of like this. This is quite useful. So B intersect A complement will be just this part. So so this probability would be the same as probability of B, the entire B minus the intersection. All right. So so that is how this that particular slides look like. All right. And so this is the numerator. The denominator, we make use of the fact that we are calculating the probability of the opposite. And so it's just plugging in the numbers. All right, and so on and so forth. Okay, so in a way, we are calculating things using basic principles, and yeah. So let me advertise one more time. I mean, that is the beauty of mathematics. Basically, we only have 3 rules, and then all the subsequent calculations are based on these 3 rules, and no other rules are needed. All right. So I think the next session is on independence. Maybe we'll have a break first, and we'll try to cover independence and the Bayes theorem for the second half of our lecture. So let's come back at 10:45. Actually, I forgot to say something in the past lecture. I really appreciate the fact that you bring up the questions either during the break or actually way back. There are occasions that some of you yell out from your seat. I think that is, I welcome this. And but occasionally I might have to stop you because I wanted to cover the material. But as long as possible, I think this is a good thing that you asked. Especially in probability, there are literally two things here and there. If you don't clear it up, it would become very big, all right? So it would be best to clear things up. Sometimes it might be the notation, sometimes it might be the assumption, or sometimes it's the setting, or sometimes some other things, all right? So I think I mentioned this because this is crucial. This is multiplication rule. Some of the textbook, especially those coming from the, sorry, I don't mean to belittle them, coming from an engineering background or coming from social science, they would think of this rule as one of the axioms of the probability. The fact is, this is not the case. It follows from the definition of the conditional probability. It is not an assumption in itself. Okay, so rearranging this, we will have the probability that A and B happen jointly is equal to probability of A given that B, yes. Okay, I know you guys are very excited, but can you tune down your volume? Okay, now I think this is algebraically, this is just a matter of rearranging the term, which is not a big deal. So I'm referring to the first one. So you are looking, this is the definition. So I'm multiplying this term over, so I will have this. Now, of course, you can just see it as an algebraic manipulation, which is not difficult at all. But I think there is a very rich interpretation of the left-hand side and the right-hand side. All right. So one of this is you think of the right-hand side. There is a time event here. There is a sequence of events that happen. Now, the left-hand side is asking that A and B have to occur at the same time, or A and B have to occur. But I can think of it as A and B are occurring, but at a different steps, okay? The first time is that I'm interpreting that A has to occur first. And after A has already occurred, I ask, now, given that A has already occurred, I want B to occur as well. So I'm basically fulfilling the left-hand side into two steps. One is I deal with A. I have to insist A has to occur. And then the second step is, given that A has already occurred, I want B to occur as well. Now here, if you're thinking of this, this is the usual in business school or is a decision tree. But people also think of it as a probability tree. So you are thinking of whether A has happened or A that has not happened, all right? And then from this, you can ask whether B has happened or B has not happened. So this is, you are thinking of a time event. And so this will be the probability of A. So the branches are labeled by their respective probability. Now, of course, we can fill this in, but this is not our focus. Our focus would be only on this branch. Okay, and now what is this? This is the probability that B will occur given that A has already occurred. Okay, so the equation here is saying that this is actually equal to A intercept B. All right. So you are thinking of this in terms of in a sequential manner. All right. Now this is our own creation in terms of the sequencing. I mean, the events happen in a sequential order. But on my left-hand side, actually, I do not have this scenario. I'm reading into the story into it. But of course, you can, A and B are symmetric here. You can actually have a similar situation. So you can have the other formula, that is probability of B. So you consider B first, and then based on whether B has occurred or not, you calculate that A has to occur. All right. So so this is just, I mean, a mental picture. All right, that you impose. I mean, you are trying to understand the equation here. Now, this is going to be the picture that we are going to explain in the Monty Hall problem as well as the Bayes theorem. I mean, that can be very useful. Now, here I only have two possible outcomes. Either A will happen or A will not happen. But I could have more branches here. And then each of the branches, I would have more here. All right? So we will use this. If you are, I think this can be quite useful mental picture of your subsequent calculations. So this rule enables us to calculate the probability that two events will both occur. The probability that both events occur is simply the product of the probability of one event occurs. The equation 1 look at A in particular. So whether A, we insist that A has to occur. And then the conditional probability that B has to occur now that given A has already occurred. So we impose a sequential order of the happening. Okay, the multiplication rule can be extended to more than two events. So maybe I'll do it in a slow motion. I'll do it for n equal to 3 first, and then you will see the situations. Okay, so n equal to 3. So maybe it's better to write A, B, C. So now I'm thinking of A has to occur, and after which B has occurred. And now by the time we get to here, A and B have already occurred. And so we want C to occur. So this is how the formula comes about. And if you're thinking of the probability tree, so this is the situation. I'm only tracking this, all right? And then so it's B, and then it is C here. So of course, if you are interested to fill it in, then it would be this, and so on and so forth, and this branch. And so the thinking here is that I'm following this branch. And this branch is probability of A, and now A has already occurred, so I need this conditional probability. And then I need this, but AB has already occurred. Okay, so basically that is the probability tree that we are thinking about. The one that is in your lecture notes or in the slide here is just, I mean, a general statement for more than n events. So what basically is the idea of doing this is you handle one event at a time, but you just can't ignore the conditioning part, okay? So the argument is this: you want all these n events to occur at this, together. So you first insist that one of them has to occur, and you call it A1. and then the second one has to occur given that the first one has already occurred. And when you are coming here, you want the third event to occur given that the first two events has already occurred, and so on and so forth. Now here the order is important. Whether you write A1, the A1 has to match with this, and then A1 intersect A2 has to match with the intersection here. But here you can rearranging the order. If you rearrange the order, you have to rearrange this order accordingly. All right, so that is the crust here. Okay, now this is a good example why we are doing it one at a time. This is like you are getting two cards from a deck of cards, but you are doing it without replacement. So you draw one card first, and then so there are now remaining 51 cards, and then you draw one more card from there. All right. So let's have an example. We'll deal two cards from a regular playing deck without replacement. What is the probability that both cards are aces? What is the probability that only one card is an ace? Now it has two questions here. And what is the probability that if three cards are dealt, they are all aces? So there are three questions here. Let's deal with the first one. Okay. So A1, A2, A3 denotes the events that the first, second, and the third card. I think we missed something. The first and second and third cards are aces. All right. So if I want both aces for the first two cards, that is the probability of A1 intersect A2, and that is the probability of A1, and that is the probability of A2 condition on A1. Now, you have 4 aces out of 52 cards, so you have to choose 4 out of 52. And then now that one card has already been chosen, so the remaining 51 cards, this is the basic assumption that the remaining 51 cards are equally likely to be drawn, all right? And so there are remaining 3 aces. So I will have 4 over 52 times 3 over 51, and that simplifies to this number. This is something like less than 0.5% of the time, all right? And so this is dealing with the first questions, and then the second questions is the probability that only one card is an ace. So we will deal with one term. So this is A1 intersect A2 complement. It means the first card is an ace, the second card is not an ace, all right? This is the other case. The first card is not an ace, the second card is an ace, all right? So let's deal with the first term and explain this. I want an ace, so I have to have 4 cards out of 52 in my first draw. Now, after I draw an ace, and I don't want an ace anymore, so I have 48 non-aces still left in the remaining deck of cards, and there are only 51 of them, so I would have 48 over 51. So this is the situation here. And similarly, in order to get a non-ace in my first draw, which there are 48, and I'm drawing it out of 52, so there is the probability is 48 over 52. And now there are only 51 cards left after one card is drawn, and there are still 4 aces left, and so I have 4 over 51. So it is actually the same number, so it's 2 times of one of them, so it is 32 over 221. And here the reasoning goes like this. In your first draw, you have 52 choices. In your second draw, you have 51 choices. And in the third choice, you have 50 choices. And now here, in your first choice, you have 4 aces that is for you to choose. And after one ace has been drawn, you have only 3 left. And then both aces have been drawn, and you only have 2 left in the remaining deck. So these are the numbers. So this number is getting smaller. So to get 3A, okay, so this is just trying to do that with a counting method. Okay, so I think I would just I'll just not explaining it here. Okay. If you want to let me know. Okay, this is interesting. The probability that a doctor correctly diagnoses a particular illness is 0.7. Given that the doctor makes an incorrect diagnosis, the patients will enter a lawsuit is 0.9. What is the probability that the doctor makes an incorrect diagnosis and the patient sues? All right. So this is a situation. D stands for correct diagnosis, and U is patient sues the doctor. But it has to be done in a sequential manner. It is given that probability of D is equal to 0.7, and also the probability that given that the doctor has made a incorrect diagnosis, and the patient sues is this probability. So we are interested to the probability that we are interested is the doctor makes an incorrect diagnosis and the patient sues. Now, one of the my suggestion to tackle this kind of story problem is after you first read through the questions, you start to define the event, all right, like this. So you define the event, and then you go back to the story, and then fill in the probability as you reread the question again, but read the questions according to your notations, all right? And so that is how you decipher the story. So now we are interested. So the question asks about this, the probability that the doctor will make an incorrect diagnosis and that the patient is suing. So we have the probability of. So now here the order of the sequence, the order of the events happen is only makes sense in this way. It doesn't make sense when you condition on the patient sue, and then the other is that the doctor will make. So the context of this problem makes which event should occur first or not is important. So you can think of the diagnosis correct or not correct are two possible causes, all right? So and then we are calculating this. So this is just the multiplication rule. We do it in sequence, okay? So we calculate the probability that the doctor will make an incorrect diagnosis is this, and then with this, all right? Now it is conditioned on the fact that he makes the wrong decisions. And so this is the opposite of making the correct diagnosis. So it would be 1 minus 0.7 here. And so this worked out to be 0.27. Now this is just an example. I think probably the doctors here will have a much better success of diagnosis. 0.7 is really low, unless it is a very rare disease. Okay. Another example, 4 individuals have responded to a request by a blood bank for blood donations. All of them forget their blood types. It's unlikely in Singapore because your identity card has your blood type on it. So all of them forget their blood types. Suppose only A plus is desired, and only one of the 4 actually has this type. All right? If the potential donors are selected at random order for typing, what is the probability that at least 3 individuals must be typed in order to obtain the desired type? Usually, I mean, it's just, you just have to be patient in reading the story. And then when you're reading the story the second time, you start to, use symbols to denote events, all right? And as you go on, and then rephrase the questions in terms of the probability notations, what you are being asked, all right? So let AI denote the event that the IV donor has an A+ blood type. So A1 means the first person, and the event that he has the blood type A+, and so on and so forth. So the probability that at least 3 individuals must be typed to obtain the desire, it means that at least 3 individuals means that it consists of 2 situations. It is exactly 3 individuals or 4 individuals, right? But another way to say it is that your first 2 situations fail, right? If your first 2 situations fail, then definitely you have to go to the third or the fourth. So this is how this probability is rephrased in this way. The first 2 donors are not of A+ type. So this is the probability of A1 complement and then A2 complement. So now why is it 2/3 here? It is because of the questions. It's a little bit not very realistic. This is under the assumption that only one and only one of the 4 actually has this type. So you basically think of 4 cards, all right? And 3 cards do not have an A+ on the card. And then there is 1 card with an A+. And so that is the situations. And so you have to draw the card one at a time, and then until you get the A+ card, all right? So that might be easier. You think of cards is a bit more reasonable. And so now you draw a card. The first one is not an A+ blood type. So that means you have 3 non-A+ cards out of the 4 that you are drawing. So it is 3/4. And you have 2/3, and this is 1/2, and so on. And so on and so forth, all right? Now there is a little bit more realistic description of the same, but not as a blood type. You think of a janitor has a set of keys, let's say 10 keys, or you yourself 10 keys, and then you want to enter your apartment. So only 1 key is possible, all right? And the other 9 keys. Somehow you do it in a random fashion. Of course, this is usually not the case, but if you are someone, if you are just given a bunch of keys, then you keep trying, right? So you randomly pick 1 key, and if it works, then that's it. If the first key that you use does not work, you set this key aside. You are not going to try again. So you get another key. So this is the scenario. I have 4 keys. Only 1 key works. And then you are choosing it in this manner. So what the question is asking you is that at least you have to have 3 tries in order to open the door, all right? So what it says is that the first 2 tries must be wrong, and that's it. So I think if you're thinking of the keys and the doors, it's a little bit more natural than blood type here. Now, inverting the order of conditioning, it says that sometimes it's beneficial to be able to swap the event of interest and the conditioning event. So the inverse of the probability. Maybe I will explain it when we come to the Bayes' theorem. So this is, again, by definition, probability of A conditioned on B. The definition is the first thing is to unconditionalize the whole thing according to the definition. So that would be the probability of A intercept B over probability of B. But now we make use of the first, we are thinking of it in a sequential manner, using the multiplication rule. So we can use this, all right? Okay, so you can rewrite this in terms of the sequence. A occur first, and then given that A has already occurred, you want to calculate this. So this is basically I use a definition of conditional probability twice. One, I unconditionalize it, and then second is I apply it to a multiplication rule. So you can see if you the probability of B conditioned on A and probability of A conditioned on B is only equal when probability of A and probability of B are equal. Because if that is the case, then the two factors here will be cancelled. And then, so if they are not equal, and if you interpret the question wrong, or the probability that you are formulating, you mess up in the which one is to condition, your answer will differ. All right. The only chance that your answer, luckily, will be the same, even though you calculate with the wrong steps, but it happens to be the same is when probability of A and probability of B are equally likely, then your mistake won't show up. Okay, mammograms. Mammograms are used to detect breast cancer. Easily available information include how often mammograms come back positive, overall breast cancer rate, and how accurate the mammogram is when the cancer is present. What these two sentences is saying is this: when you devise your mammogram and test how accurate the mammogram is, you have to do it in these two steps: the calibration of the diagnostic test. You have to have an independent assessment of a woman with breast cancer. All right, and then so these are your subjects, and then you let them go through the mammogram and see how many of women with breast cancer are being tested positive using your test. So suppose you have 1,000 women with breast cancer, and then so if the test indicate 900 times, so your test is only 90% accurate. All right. So this is accurate in the sense of picking up the disease. So this is what we call sensitivity. There is another dimension of looking at the test. The test is when a woman without breast cancer is being tested by the mammogram should say that it is negative rather than positive. But diagnostic tests sometimes make mistakes. So again, they would get an independent assessment, 1,000 women known to have no cancer, no breast cancer, and then ask them to go through the mammogram. And if 950 of them are being reported to be negative in the mammogram, then the test is 95% accurate, and this is called specificity. All right, so we have a different name for this. So this is this. The probability of positive test. I think what I'm telling you is will come later. All right, but this is a more hypothetical situations. We know that the probability of positive test is 0.107, and that the probability of having cancer is 0.1, and that the probability of positive test, given that it's cancer, is this. Okay, what is the probability that when the mammogram is positive will be worked out in this way? The probability of cancer, given that it is positive test, we want to invert the two conditional probability. So we have to use the formula earlier. this is B on A and A on B. We change it. I think we make a mistake, right? The equal sign should go to the next line. All right, so this is 0.8 times 0.1 and over 0.107, and then the whole fraction is equal to 0.748. Now this is the thing that we will be most interested. The test usually is supplied by pharmaceutical company, and they would calibrate the sensitivity and specificity that I just mentioned. Sensitivity is among those who known to have cancer is being tested positive. Specificity means among those who do not have cancer will be reported as negative. Now, but this is just the tool itself. But for someone undergoing the diagnostic test, this is the most interesting thing. If you are tested positive, you want to assess whether you have cancer, right? Okay, so we will come back to this in a later session after we introduce a Bayes theorem. Okay, but there is a very, very important concept called independence. Now, independence is very peculiar in probability. Everything else is like analysis, I mean, in your calculus or whatever. Actually, when probability becomes a branch of mathematics, if you remember the story, when Kolmogorov introduced it, I mean, the other mathematicians will laugh at the probabilists. I mean, so it is, they will label the probabilists as analysts with an extra concept of independence. All right, so independence is, I mean, something that we are thinking of in probability, which is seldom used in analysis, and they do not capitalize it. So the concept of independence, so it is one of the most important concepts, and is usually very much abused. All right, in a lot of computations, people make the mistakes of assuming independence when they are not. Okay, two events are A and B are independent if and only if the probability of the joint event is equal to the probability of the product of the probability of single event. And two events A and B are not independent if this is not true. All right. Now, the common mistake among many of you who first learned the definition is you are not aware that you are applying a circular argument. So basically, we want to prove the left-hand side equal to the right-hand side. So the right-hand side, usually the individual numbers are given to you. And so when you want to calculate this, the first thing you do is you multiply the two probability. And then you take this as the probability of the joint event. And this is where the mistake is, or the circular argument. You basically use an equality to calculate the left-hand side, and then later on to check that it is equal. Of course it is equal. Okay, you are not doing. So what you have to do is calculate this probability of the intersections in a separate manner, not calculating by the right-hand side. And then really verify whether the product of this individual probability is equal to the probability of the intersections. Okay, maybe let me first explain why do people call it independent. All right, and okay, we are interested in this. We are interested in the event B. All right, so here we have no information about whether A has occurred or A has not occurred. So it is not known to us, all right, this side. But this side is saying that I have some extra information. The information I have is that A has already occurred, all right? Now, so let us unconditionalize it as before. Okay, this is where assuming independence. So that would be the probability of A multiplied by, and so this cancel out. So if I assume independence, this probability turn out to be equal to this, under this assumption. All right. Now we have an interpretation of this, because the right-hand side says that I'm ignorant about whether A has occurred or A has not occurred. Whereas on my left-hand side, I have extra information that A has already occurred. But the fact that they are equal means that whether A has occurred or not occurred will not change your probability that you assign to B. So this is actually what we meant by independence. Knowing whether A has happened or not has nothing to do with the way you assess the probability of B. All right? So that is the meaning of the probability. Now, of course, this interpretation has a drawback, because in here I will have to assume a probability of A is positive in order to understand this. But the definition here is free from these conditions. Now, as a side remark, suppose the probability of A is 0, then the right-hand side has to be 0. We have seen something similar before. A intercept B is a smaller event than A, so it would force the probability of A intercept B to be 0 as well. So as long as probability of A is 0, A and any other B will be independent. Okay? Another thing is, if probability of A is equal to 1, we can show that A will be independent of any B. All right. So in the extreme of A, the probability is 0, then A will be independent of anything. And if probability of A is 1, A will also be independent of any other event. Okay. So here it is. I think I've done the little proof there. So, but the interpretation is that having knowledge that one event happens does not change the probability of the other event. So knowing this extra information, whether that particular event happened or not, is irrelevant, basically. All right. Now, in probability calculations, we like independence. But in science discovery, we actually do not want independence. Because suppose you want to see whether smoking, you want to investigate a certain situations, and if the other conditions is independent of whatever you are investigating, then the condition is irrelevant to your study, and so you are not going to have any discovery. Okay, 2 dice. I roll a pair of dice. We assume they are fair. And A6 denote the event that the sum of the 2 dice is 6. And B denote the event that the first die is 4. Okay. To get to 6, the sum, you only have 1, 5, 2, 3, 3, 4. Okay. To get to 6, you have 1, 5, 2, 4, 3, 3, right? And then 4, 2, and then 5, 1. So you have 5 such situations, all right, out of 36. Okay, and the fact that the first die equal to 4, meaning that you have no restriction on the second die. So there are 6 of this. 4, 1, 4, 2, 4, 3, up to 4, 6. So it's 6 over 36. So this is 1 over 36. Now here you have to calculate the intersection separately. Okay, so you don't multiply this and then check whether it's equal. It would be equal if you do this. A6 of intercept B means that the sum is 6 and that the first one is a 4. So you have to force the second one has to be a 2. There is only one such outcome, and it is 1 over 36. So if you multiply these two numbers, this would be 5 over 216. And here, if you change it to the same denominator, it is 6 over 216. So they are not equal. What it means is that if you know something about the first die, whether it is equal to 4 or not equal to 4, it affects your sum. Okay, now the sum of a pair of dice can be 2, can be 3, can be 4, and so on, up to 12, right? I want you to try changing this into A2, A3, up to A12, and see whether knowing the first die, will it affect the sum. Let me motivate you. One of this situation is an anomaly, all right? So there is one situation that differs from the rest, all right? Oh, okay, it's here, all right? So if the sum is 7, then this will be 1 over 6. This is the only change, all right? So this is 7. To get a sum of 7, you have 1, 6, 2, 5. To get a 7, yes, 1, 6, 2, 5, 3, 4, 4, 3, 5, 2, and 6, 1. So there are 6 of this, all right? And the probability of getting a 4 in my first die has been calculated, is 1 over 6. And again, if I know the sum is 7 and I know my first die, then of course I will know my second die. And so I only have 1 over 36. And so if you verify it, they are equal. So meaning that if you are looking at the sum, whether you know the first die is a 4 or not a 4, won't help you. All right? So they are independent. But if the sum is something else other than 7, 2, 3, 4, 5, 6, 8, 9, 10, 11, 12, it matters. For example, if you want the sum is 2, but you know the first die is 4, then it is not possible, right? Okay, so this is a little strange thing here. All right. Okay, cards without replacement. This is where the independence is. Because basically, independence is you are doing it in a very rigorous manner, and then the situations is the same. So in order for it to be the same, you have to replace the card. Okay, so let me see whether I have time. Maybe I think I'll just stop here. But I wanted to, so maybe I'll just stop here. Yeah.